Right now, while you're listening to this, there's a lock on everything you own. Your bank, your messages, that little padlock in the corner of the screen when you type in a password. And here's the strange part. The lock isn't really a secret. A thief can stare straight at it all day long. It's a math problem. A problem so monstrously hard that every computer on Earth, grinding away without a break until the sun itself burns out, could not crack it. That is the lock. That is the thing keeping the whole world's secrets safe tonight. And in 1994, one quiet mathematician wrote down a recipe, a set of instructions for a machine that did not yet exist, that cracks that lock before lunch. The machine still isn't finished, but the recipe is out there, and the clock has been running ever since.
It has. And I want to sit in that for a second, because most people never feel it. You lean on that lock your whole life. Every time you tap your card, every time you send a message you'd rather no stranger read, and you trust it the way you trust the floor to hold you up. And it does hold. Today it holds beautifully. What almost nobody carries around is that its safety isn't a law of nature. It's a bet. A bet that a certain sum is too hard to do backwards. And in 1994, someone showed the bet has an expiry date.
An expiry date. Okay, I want the whole story of that. But last time, you and I spent the entire episode on one idea, and you told me it was the key to everything that comes after. Interference. Remind me, because I have a feeling we're about to cash it in. The one trick everything is built on.
We're about to cash it in completely. So let's put it back on the table. Last time, the big turn was this. The secret of a quantum computer is not that it tries every answer at once. That's the myth, and it's a lovely myth, and it's wrong. The real secret is quieter and far stranger. A quantum computer runs all the possibilities as a kind of wave, a blend with amplitudes, the way we built up 2 episodes back. And then it arranges for the wrong answers to cancel each other out, to erase themselves, so that when you finally look, the only thing left standing is the answer you wanted.
Right, that was the line that stuck with me. The wrong answers erase themselves. Like waves on water, where a crest meets a trough and they flatten to nothing.
Exactly like that. Crest meets trough and you get calm. That's destructive interference, and it is the whole game. Now, last time I showed you that trick on a toy. A made-up little puzzle with no purpose in the world except to prove the trick was real. Today I want to show you the 2 times somebody pointed that same trick at a problem that actually matters. And the world has not been quite the same since.
2 algorithms.
2 algorithms, and they have completely different flavors, which is why I love teaching them together. The first one is a needle in a haystack. It's about searching, finding one thing hidden among a mountain of things. It's the gentler of the 2, and it's a beautiful warm-up. The second one is the lock breaker. It's about undoing a piece of arithmetic that the entire internet is betting can't be undone. That's the one with the countdown clock on it.
Let's take the gentle one first. Warm me up, Grover, the needle in the haystack.
So picture the most boring, hopeless search you can imagine. I hand you a phone book, an enormous one, a whole city. But I've played a trick on you. You don't have a name, you have a number. A phone number, and you want to know whose it is.
Ah, and the phone book is sorted by name. So the numbers are just scattered through it in no order at all. There's no clever way to jump to the right page.
None. The numbers are in total chaos as far as your search is concerned. So what do you actually have to do?
I have to start at the front and read every single entry. Check 1. Nope. Next. Nope. Next. All the way through until I hit it. There's no shortcut. I just grind.
You just grind. And on average, if the number's sitting somewhere random in there, how far do you get before you find it?
About halfway, I suppose. Sometimes I get lucky and it's near the front. Sometimes it's dead last. But on average, I've chewed through half the book before I hit it.
Half the book. Hold on to that number because it's the thing we're going to demolish. If the book has 1 million entries, you're doing about 500,000 checks. If it has 1 trillion, you're doing about 500 billion. The work grows straight in step with the size of the pile. Double the haystack, you double the searching. That's the classical curse, and it feels utterly unavoidable. Of course, you have to look at things to search them.
It feels like the definition of searching. What else could searching even be?
That's the right thing to feel, because the way out is startling. But first, one extra ingredient this problem needs, and it matters. You may not know where the answer is, but you can recognize it the instant you see it. Show you the right entry and you go, yes, that's the one. You'd know it if you found it.
Sure, like a password. I can't guess your password, but if you type it in, the computer knows in a heartbeat whether it's right.
That's the perfect example. Hold on to it. Hard to find, instant to check. That gap is exactly the kind of problem this algorithm feeds on. So, a man named Love Grover asked, what if I don't grind through the haystack one straw at a time? What if I make the whole haystack into a wave?
Here we go. So, back to superposition. I load every entry in the phone book into the machine at once, as a blend. All of them together, humming along as one quantum state.
All of them at once. And now here's the trap I want you to walk straight into, because everybody does. You've got all million entries loaded up in there together. Isn't the answer just, in there? Can't you read it out?
I feel like the answer is no. And it's going to be for the reason you drilled into me last time. If I just look, if I measure it right now, I don't get the answer. I get one entry picked completely at random out of the million, because they're all in there with the same tiny amplitude.
You've got it. You just measured, and the universe handed you a random straw out of the haystack, which is exactly as useless as reaching in blindfolded and grabbing one. Loading everything in is nothing on its own. Superposition, all by itself, buys you precisely 0. This is the misunderstanding at the heart of nearly everything people believe about these machines, and I want to nail it to the wall. Having all the answers in the box is worthless unless you can bend the odds so the right one is overwhelmingly the one you pull out.
So the entire art is in that bending. Loading the haystack is free. Making the needle the thing you actually grab, that's the trick.
That is the whole trick. So let me show you how Grover bends it, and I'm going to do it with a picture you can hold in your hand. Imagine every entry in the phone book as a little bar, standing up in a row. 1 million bars, side by side, and right now they're all exactly the same height, because every entry has the same little amplitude. A flat field of identical bars stretching off to the horizon.
Okay, 1 million identical bars, dead flat. And somewhere in that row is the one I want, but it looks exactly like all its neighbours.
For now. Grover's move has 2 steps, and he just repeats them over and over. Step 1, he marks the answer. Remember, you can recognize it, so the machine reaches in, finds the one bar that's the answer, and flips it. Pushes it down below the line, so instead of sticking up like all the others, it now hangs down. It's the only one pointing the wrong way, a secret tag.
So now the field of bars is still flat and identical, except one lonely bar is hanging down underneath. Everything else is unchanged. But wait, if I measured now, I still wouldn't get it, right? Flipping it down doesn't make it bigger. It's still the same size, just pointing the other way.
Perfectly reasoned, and that's why there's a step 2, and step 2 is the miracle. Step 2 is flip everybody around the average.
Around the average. Okay, you're going to have to walk me through that one slowly.
Slowly it is. Take the average height of all the bars, the water level, the mean. Now, because almost all the bars are standing at the same height up top, and just one is hanging down below, that average sits a hair below the top row. just a whisker below where the crowd is, yes?
Yes, one bar dangling down barely drags the average down at all when there's a million of them up top. So the average line is just a smidge below the crowd.
Now here's the move. Reflect every single bar across that average line. Whatever a bar's distance is above the line, send it the same distance below, and the reverse. Flip the whole field across the waterline. What happens to the crowd? The bars sitting just a smidge above the average.
They're barely above the line, so when I flip them across it, they end up just a smidge below. They barely move. They stay roughly the same height.
They barely twitch. And now, the one bar that was hanging way down below the line, the marked one, it's far below the average. So when you reflect it across,
It shoots way up. It was hanging far below the waterline, so its mirror image is far above it. It springs up tall, taller than everyone else.
it springs up above the whole crowd. In one pair of steps, mark it, then flip everyone about the average, the needle went from lost in the field to a head taller than the entire haystack. And you don't stop. You do it again. Mark, flip about the average. Mark, flip about the average. And every single round, that one bar grows, and everyone else shrinks down.
So it's not one magic step, it's a nudge, repeated. Each round leans the odds a little further toward the answer.
A nudge, repeated. And here's the other way to see it, the one that gives the trick its name. Instead of bars, picture a single arrow, a pointer, starting out aimed almost completely away from the answer, because right now the answer's drowned in a million wrong ones. Every round of mark and flip rotates that arrow a notch, a small, steady turn, tick, 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 away from the sea of wrong answers and toward the one right one. That's why people say you rotate the arrow toward the answer. You're not searching, you're steering.
Amplitude amplification. That's the phrase, isn't it? You take the amplitude of the answer, which started tiny, and you pump it up, round after round, while the wrong ones bleed away.
That's the name and that's the substance. The wrong answers interfere destructively. They eat each other, they cancel, while the right one builds. It is last episode's trick, aimed at a haystack. Now, the question you should be dying to ask.
I am. How many rounds? Because if I have to nudge that arrow a million times to find one thing in a million, then congratulations. We've built a fantastically expensive way to do exactly as much work as the boring phone book.
Right, if it took a million nudges, I'd have wasted your evening. Here is the punchline, and it is one of the loveliest numbers in this whole field. To find your needle in a haystack of a million, you don't need a million rounds. You don't need 500,000. You need about 1,000.
1,000 out of a million.
About the square root of the size of the pile. That's the rule. Whatever the haystack is, you need roughly the square root of it. A million has a square root of 1,000. A trillion, a million, has a square root of a million. So a search that would have cost you 500 billion boring checks now costs you about 1 million clever ones.
Hang on, let me feel the size of that. 500 billion down to a million. That's not shaving a bit off. That's the difference between a job that takes years and a job that takes a blink.
That's the difference between hopeless and easy for a big enough pile. And notice how general this is. I never told you what was in the haystack. Phone numbers, passwords, puzzle pieces, a needle in literally any unstructured heap. As long as you can recognize the answer when you see it, this trick shrinks the search to its square root. It doesn't care what the haystack is made of.
Okay, that's genuinely gorgeous. But you called this the gentle one. Square root, turning a million into 1,000. That already sounds world-ending to me. What could possibly be more dramatic than that? The catch in the gentle one, and why the next one is worse.
I love that you're impressed, because I'm going to gently take some of it back. Not much. A square root is a big win, but it's a tame win. Watch. Make the haystack 100 times bigger. How much more work is the classical grind?
100 times bigger haystack, 100 times more grinding, straightforward.
And Grover?
The square root of 100 is 10, so 10 times more work. Instead of 100,
10 instead of 100. So yes, Grover wins, but as the haystack grows, the cost still grows, just far more slowly. Make the pile astronomically bigger, and Grover's job gets astronomically bigger too, merely square root astronomically. A spectacular discount, not a free lunch. There's a ceiling on the magic, and we'll spend a whole episode next time being honest about where it sits.
So Grover is, everything gets easier, but nothing gets trivial. The mountain shrinks to a hill. It's still a hill.
Beautifully put. The mountain shrinks to a hill. Now brace yourself, because the second algorithm does something a square root can only dream of. The second algorithm takes a mountain that would take longer than the age of the universe to climb and turns it into an afternoon stroll. It doesn't shrink the mountain, it makes the mountain evaporate.
And that's the lock breaker, the one from the cold open, 1994.
That's the one. Peter Shaw. And to feel why it's such an earthquake, you first have to understand the lock it breaks. Let's leave the haystack behind. Let me teach you the most important one-way street in the modern world. Why multiplying is easy and unmultiplying is agony. Here's a question that sounds like it's beneath us. Is multiplying two numbers easy or hard?
Easy. I mean, tedious for big ones, but easy. I learned to multiply big numbers when I was a kid. You just do it. Line them up, grind through the steps, out comes the answer. Boring but simple.
Boring but simple. Even for enormous numbers, hundreds of digits long, a computer multiplies them in the blink of an eye. No sweat. Now the reverse. I hand you the answer, one big number, and tell you it was made by multiplying two other numbers together. And I ask, which two?
Oh, that's completely different, isn't it? Multiplying forward, I've got the two ingredients and I just combine them. But going backward, you've handed me the cake and asked me which two eggs went in. I have to figure out what was multiplied to get this thing.
The cake and the eggs. Exactly. And here's a sharper version, mixing paint. I give you a can of yellow and a can of blue and say, stir them together. Easy. You get a very specific green, instantly. Now I hand a stranger that green and say, tell me exactly which yellow and which blue I started from. What shade, what amount, precisely.
That's a nightmare. There are 1,000 yellows and 1,000 blues that could have made roughly that green. They'd have to sit there mixing test batches forever trying to match it.
Forever. Mixing is a one-way street. It's trivial going in and agony coming out. And numbers have their own version of exactly this. Multiplying is stirring the paint. Unmultiplying, the proper word is factoring, finding which pieces were multiplied together. Factoring is unstirring it. And for the right kind of number, unstirring is so hard it may as well be impossible.
But hang on, numbers aren't paint. Paint blurs together, it's mushy. Numbers are exact. Surely with numbers I could just try things. Try dividing by 2, by 3, by 5, work my way up until something fits.
You could. And for small numbers it works fine. That's why your intuition rebels, because you've only ever unmultiplied small numbers in your head, and it felt easy. But feel the scale. The numbers that lock the internet are monsters, hundreds of digits long. To unstir one by trying divisors, you test a mountain of possibilities so vast that if you put every computer on Earth on the job from the birth of the universe until now, they wouldn't be close to done.
The whole planet's computers. the whole age of the universe, and not close.
Not close. And that ridiculous, gaping difference between how easy it is to multiply and how impossibly hard it is to unmultiply is not a nuisance. It is the foundation. Someone built the world's locks on top of that gap, on purpose. The lock the whole world leans on.
Okay, so show me how you turn unmultiplying is hard into an actual lock on my bank account. How does a hard sum keep a secret?
Here's the shape of it, and it's genuinely beautiful once you see it. You pick two enormous prime numbers, two numbers that are your private secret that you tell nobody, and you multiply them together. Stirring the paint, easy. Out comes one giant number, and that giant number you publish. You paint it on your front door. You hand it to the entire world. Anyone at all can see it.
Wait, I publish it? The number that's built out of my two secrets, I just give it away to everyone?
You give it away freely, because the giant number is the lock, not the key. Anyone can use it to scramble a message that only you can unscramble. The scrambling uses the public number, the one on your door. But the unscrambling needs the two secret ingredients, the two primes you stirred together to make it. And to get those back out, a stranger would have to unstir the paint. Factor it, which we just agreed is hopeless.
So the whole world can lock things to me using the number on my door, but only I can open them, because only I know which two pieces I multiplied to make that door in the first place.
That is the entire idea. And a version of it, a public number everyone sees, two secret factors only you hold, runs underneath nearly every private thing you do on the internet. It's in that padlock in your browser. It's the strongest everyday encryption there is. Uncountable secrets ride safely on one bet, that nobody, no matter how much computing power they own, can unmultiply a big enough number in any reasonable time.
And it's held. The bet has held.
For decades, the bet has held perfectly. The cleverest mathematicians alive have tried and tried to find a fast way to unstir the paint, and they've come up dry. As far as ordinary computers are concerned, the lock is real and the lock is safe. And then, in 1994, Peter Shaw said 7 terrifying words, in effect. What if the computer isn't ordinary? Shaw's sideways door, the hidden rhythm.
All right, so how does a quantum computer unstir paint that the whole planet couldn't unstir? Does it just try all the devices at once? Because you told me an hour ago that trying everything at once is the myth.
And I meant it. And here I get to prove it. No, Shaw's algorithm does not try every possible factor at once and sift out the right one. If that's all it were, it'd fall into the same trap Grover taught us. You just measure and get garbage. Shaw's genius was that he didn't attack the lock head-on at all. He found a secret side door. He connected unmultiplying to a completely different-looking question. A question about rhythm.
Rhythm, as in music?
As in repeating patterns. Cycles. Let me build you the rhythm, because it's the heart of the thing. Pick your giant locked number, the one on the door. Now pick some other number, doesn't much matter which, call it your starting note, and start multiplying it by itself, over and over. The note, then the note times itself, then times itself again and again. But each time, you do one extra thing. You divide by the giant number and keep only the remainder. You throw away the whole part and keep just what's left over.
So it's like a clock. On a clock, you count up. But when you pass 12, you wrap back around to 1. You only ever keep the remainder. 13 o'clock is just 1 o'clock again.
A clock is precisely the right picture. A clock whose face is that giant number. You keep multiplying, and every time you'd shoot past the top, you wrap around and write down where you landed. So you get a long, long trail, where you landed after 1 step, after 2, after 3, marching along, wrapping around this enormous clock face apparently at random.
Apparently at random, but I'm guessing it's not actually random.
It is not. And this is the little miracle at the center of everything. That trail of remainders, it repeats. Sooner or later, it comes back around to where it started, and then it does the exact same dance all over again, on a loop. It has a cycle length, a period, some number of steps after which the whole pattern comes back and repeats, like a song with a verse that eventually returns to the top.
Okay, and let me guess why you care about that period. You're about to tell me that the length of that repeating cycle secretly knows the answer to the unmultiplying.
That's exactly what I'm about to tell you, and it still gives me a chill. This is a fact from deep in the theory of numbers, known long before quantum computers were a gleam in anyone's eye. If you can find the length of that repeating cycle, just the length, how many steps until it loops, then a little bit of ordinary schoolbook arithmetic on that length hands you the secret factors of the giant number. The two primes fall right out. Finding the rhythm is breaking the lock. They're the same problem wearing different clothes.
So the entire monstrous task, unstirring the paint, cracking the lock the whole internet leans on, Shaw quietly swaps it for find how long this repeating pattern is before it loops.
He swaps it for a rhythm-finding problem. And you should immediately be suspicious, because I've been telling you these locks are unbreakable. So there has to be a catch. And there is.
There's always a catch. Let me guess. Finding the rhythm is also hard.
On an ordinary computer, brutally hard. Because that cycle can be astronomically long. Not a verse that repeats every 8 bars. A song whose verse is so long you could listen for the entire age of the universe and never once hear it come back to the beginning. To find the period the boring way, you'd step through it, writing down each remainder, watching for the pattern to return, and it won't return in any lifetime. So the side door is bolted shut too, for an ordinary computer.
Of course it is. So we're right back where we started. One impossible problem swapped for another impossible problem.
For an ordinary computer, yes. But here's why Shaw bothered to make the swap. Finding a hidden rhythm, a repeating pattern, turns out to be the one thing in all the world that a quantum computer and its interference is magnificently built to do. This is the moment last episode was quietly preparing you for. Everything comes together right here, where interference does the impossible.
Okay, this is the payoff. Take it slow.
Slow and careful. Step 1. And you already know it's not enough on its own, the quantum computer runs the whole trail at once. Every step around the giant clock, every remainder, loaded up together as one great wave, humming along in superposition all at the same time.
And, same as the haystack, if I just measure that now, I get one random step off the pattern, which tells me nothing. So loading it up is free and useless, again.
Free and useless, again. You've truly learned the lesson. Measuring now gives you one meaningless snapshot. The rhythm is in there, woven through the whole wave, because the wave was built by that repeating process. But you can't see it by looking, any more than you can hear a song's tempo in one frozen instant of sound. So we don't look. We run the whole wave through a very special machine. And the only honest way I can describe it is a prism, but for rhythm.
A prism for rhythm. Unpack that.
You know what a glass prism does with light. White light goes in, a smear of everything, and it spreads out into separate, pure colors. It takes a jumble and sorts it by frequency. Now your ear does the same trick with sound. Somebody plays a big, messy chord on a piano, a dozen notes at once, and it reaches you as one chaotic wobble of air, a total mush. And yet your ear picks it apart. That's a C, that's an E, that's a G. Jumble in, pure pitches out. That's exactly what this quantum machine does. It takes the whole tangled wave and sorts it by rhythm.
And when it sorts the wave by rhythm, the one true rhythm, the real period hiding in there, That's the pitch that rings out?
That's the pitch that rings out. Here's what actually happens, and it is last episode made flesh. As that wave passes through the machine, all the countless wrong rhythms, all the periods it isn't, they interfere with each other. Crest meets trough. They cancel. They erase themselves exactly as I promised you they would, and they fall silent. And the one true rhythm, the real cycle length, every part of the wave that agrees on it, reinforces, piles up, adds together, and comes ringing out loud and clear above the silence. The wrong answers cancel. The right one sings.
So the interference isn't a side effect, the interference is the sorting. The cancelling of all the wrong periods is how the true one gets picked out.
The cancelling is the computation. That's the whole soul of it. And now, only now, you measure. Because everything wrong has erased itself and only the true rhythm stands tall, out pops the period. The length of the cycle. Then you do a scrap of ordinary arithmetic on it, the kind that fits on the back of an envelope, and out fall the two secret primes. The paint unstirred. The lock open.
Let me say it back to be sure I've got it and I'm not just nodding. It never tried all the factors. It never even tried all the rhythms. It loaded them all in as a wave, then made every wrong rhythm cancel itself to silence, so the only thing left to hear was the right one. That's not trying everything, that's sculpting a wave until the answer is the only sound in the room.
Sculpting a wave until the answer is the only sound in the room. I could not have said it better. And notice, it's the same sentence I'd use for the haystack. Grover rotated an arrow until the needle stood alone. Shaw made the wrong rhythms cancel until the true one rang alone. Two utterly different problems, searching and unmultiplying, and underneath, one single trick. The trick from last episode, wielded two ways. Make the wrong answers erase themselves. Everything else is detail. The chill.
So let me come back to the countdown clock, because that's where we started. And now I think I can actually feel it. This rhythm trick, unstirring the paint by listening for the hidden pitch, how fast is it compared to the age of the universe grind?
This is the earthquake. The ordinary grind, we said, would outlast the universe. Shaw's method, on a suitable quantum machine, unstirs that same giant number in something like an afternoon, maybe less. The mountain that could not be climbed in the lifetime of the cosmos becomes a gentle walk before dinner. That is not a discount, like Grover's square root. It's a different category of thing. It doesn't shrink the impossible. It abolishes it.
So every lock we just spent 20 minutes admiring, the padlock in the browser, the thing guarding my bank, the strongest everyday encryption there is, all of it rests on a bet that Shaw just wins.
Every one of them. The instant a big enough, clean enough quantum computer exists and runs Shaw's algorithm, the giant number on your door gets unstirred back into its two secret primes, and the lock simply falls open. Not picked, not forced, dissolved. And that is why I said, at the very top, that in 1994, somebody quietly put a countdown clock on every secret on the internet.
But okay, hold on, this is the part I have to press. You keep saying, when the machine exists. It doesn't exist. You told me in the cold open the machine still isn't finished. So is this a real danger or a beautiful ghost story? Am I actually in trouble tonight?
Tonight? No. And I want to be honest with you the way I always am, especially when honesty is less exciting. The quantum computers that exist right now are nowhere near big enough or clean enough to run Shaw's algorithm on a real internet lock. Not remotely close. They are small, and they are desperately fragile. And why they're so fragile is the whole crisis we walk into a couple of episodes from now. Nobody is unstirring your bank's paint this evening. The recipe from 1994 is a recipe for a machine we are still, painstakingly, trying to build.
So I can breathe.
For tonight. But here's the twist that keeps the serious people up at night, and I won't soften it because it's real. A secret you send today doesn't only need to be safe today. Some secrets need to stay secret for decades, and nothing stops someone from quietly recording your scrambled message right now, locked as it is, and simply filing it away, storing it, waiting. And then, on the day the machine is finally finished, pulling out everything they hoarded and unstirring all of it at once.
Oh, so the clock isn't only ticking on future secrets, it's ticking on today's. Anything I send now that has to stay hidden for 20 years is already, in a sense, exposed. It just hasn't been read yet.
Harvest today, read later. That's the grim little phrase for it, and it means the countdown is genuinely running now for anything meant to last. Which is exactly why, the hopeful half, the world isn't sitting still. Quietly, the locks are already being changed. Mathematicians have built new kinds of locks, on different sums, ones we believe even a quantum computer can't unstir. And the great, unglamorous work of swapping the whole world over to them has already begun.
So there's a race, the machine that breaks the old locks, being built on one side, and the new locks going up on the other. And nobody's quite sure which finishes first.
That's the race, and it's happening right now, mostly out of sight. And there's an even stranger card still to play. A way to build a lock not out of hard sums at all, but out of the raw laws of physics, so that the very act of eavesdropping wrecks the message. But that leans on entanglement, and it's a whole episode of its own, further down the road. The beauty underneath the chill.
You know what's getting under my skin here? And it's not the fear, it's the beauty. We started with waves on water. Crest meets trough and you get calm. The plainest thing in the world. And that same little fact, that waves can cancel, is the thing that finds a needle in a haystack the size of a planet and unstirs the paint the whole internet swore couldn't be unstirred. It's the same fact.
It is the same fact, and that's the thing to carry out the door tonight. Not the fear, the unity. There's no separate, exotic search magic and code-breaking magic. There's interference, waves that add and cancel. We've known about that since somebody first watched two ripples cross on a pond. What 1994 really announced is that somebody figured out how to make information itself ride on those waves. And the moment information rides a wave, computation gets a move that plain, cold logic never had. It gets to make the wrong answers cancel.
And that lands us right back at the very first thing you ever told me in this whole series. Information is physical. It's not floating abstract math in some other realm. It's built out of the stuff of the world, and it has to obey the world's physics.
Straight back to the root. Information is physical, so if the physics has waves, then information has waves, and if waves can cancel, then answers can cancel. Grover and Shaw aren't two clever software tricks somebody thought up at a desk. They're what computation looks like once you take seriously that it's a physical thing, running on a physical world, and that world is quantum all the way down. That's the whole promise of this season, and tonight you saw it pay off twice.
Awe and a chill in the same breath. The lock on my door tonight still holds. You've told me that honestly, and I believe you. But I'm never going to look at that little padlock the same way again. Because now I know it isn't a wall, it's a bet. And I know the exact year somebody worked out how to win it.
1994. A quiet result in a quiet paper that turned every secret on the internet into a thing with an expiry date. And notice, the machine to collect on it still doesn't exist. Which should make you feel powerful, and it should make you a little uneasy, both at once. That's the right place to be standing.
And I can feel you reaching for a pin to leave in me, so go on, because after all this, a search that shrinks a planet-sized haystack, a codebreaker that abolishes the impossible, I'm sitting here thinking a quantum computer can just do anything, solve anything. And something in your face tells me that's the exact thought you want to take a hammer to next time.
You read me perfectly. That's the myth that grows straight out of a night like tonight's. You watch it break the unbreakable twice, and you think it's a magic wand that dissolves every hard problem in the world. And it is not. The most important word in this whole series might be the one I've been saving. No. There are things these machines cannot do, enormous, important things, and the honest map of where the magic stops is every bit as beautiful as the magic itself. Maybe more.
So next time, you take the wand away from me.
Next time, I take the wand away, gently, and I show you why it was never a wand at all. Why the cancelling trick only works when the problem has a secret rhythm to it, like Shaw's did, or a needle to rotate toward, like Grover's. And why, for most hard problems in the world, there's no rhythm to find and no arrow to turn, and the whole trick quietly does nothing. The needle, the lock, and then, honestly, the wall. That's next time.
The wall. Good. Because I came in tonight thinking I understood what a computer was, and I'm leaving thinking a soap bubble and a broken lock are the same idea. Leave the pin in. I'll be turning that one over for a while. Good night.
Good night. Go and look at that little padlock. It's braver than you knew, and it's on a clock.